So I would, of course, like to thank the organizer for setting up this meeting. It's been very nice. And also for inviting me. Of course, I'm very lucky to be here. And today I'm going to talk about climate change. And I will talk about theoretical models based on evolutionary game theory to deal with the problem of cooperation in climate change. And this work has been done in collaboration with Francisco Santos and my PhD student Vitor Vasconcelos, who has been working almost exclusively on climate change. So the layout of my talk will be, I will discuss a little bit, so most of the first part has been already addressed here, so the global warming, public goods, and reaction towards risk, some experimental results, and then I will try to address these problems from a theoretical perspective. And there are a couple of things I would like to tell you about. I would like to study the impact of risk and of scale. I'll be more precise as we go on climate agreements. I would like to discuss this issue of collective action and the threshold uncertainty. This is a problem that is very much in the headlines recently. Nature, just the last issue of Nature, dedicated quite a bit of space to discuss this problem of threshold uncertainty. Then there's the problem of wealth inequality and homophily. We've heard already about homophily. I will discuss the role here in the context of the model. And then I will also discuss sanctioning institutions and their role in climate change governance. And we've heard already a lot about peer punishment, pool punishment. I will talk a little bit about pool punishment in different ways in connection with climate change. I have to apologize because I have 40 minutes. I have a lot of things to say, so I will fly through the details. So don't be surprised if you don't understand part of the details, but I will be very happy to discuss with any of you all the details of what is hidden in the results. Okay, there are lots of things that will be really too fast and will take too much time to explain. So the basic premise of this talk is that, of course, to solve the challenge or to meet the challenge of minimizing climate change, it actually requires cooperation. And the cooperation that we are talking about here is a problem of collective action that has been already pointed out, can be recast in the form of public goods games, which are just a specific case of n-person games, and which have, as we all know, associated processes like the tragedy of the commons. So you can think that if we need to cooperate to overcome the tragedy of the commons, and that would be the idea to solve the problem of climate change. So up to now, we've seen through the years quite a few global summits trying to break a deal in making all countries agree on mitigating the effects of greenhouse gas emissions. But the general idea is that actually they have been not very successful, and the main reasons attributed to their failure have to do with this idea that the overall perception of risk, so country leaders usually argue that the risk is not so high, we are not too sure about the targets that we should actually meet. On the other hand, the institutions that have been set up, and one of them is, of course, the United Nations, they are not able to sanction those peoples that do not abide to agreements, even if they sign the agreements. And there have been quite a lot of cases like that. And of course, then there are conflicting policies when it comes to rich and to poor countries. This is a very simplified concept, because actually there's even disagreement among the rich countries and also among the poor countries, but certainly there's a problem on how to deal with the same issues regarding rich and poor countries. And this is just a very short list. There are many other problems that can be addressed in this context. Now, the issue is that ultimately, at the end of the day, we all have to do our share to solve eventually, or to try to mitigate this problem. But what has been attempted up to now mostly has been to sit down at the same table, the country leaders, and try to make them break a deal. The question is that this is actually not necessarily going to be like that in the forthcoming years. There are very good reasons to think that the situation may change. It could be actually the people that could maybe discuss these agreements could be regions, could be actually cities. If you think that in 30 years, more than 70% of the population will be living in big cities, maybe cities will be playing a major role in this discussion. So this idea of sitting countries together is maybe going to change in the forthcoming future. So this point poses the problem of scale. At which scale should we actually try to strike an agreement? And this will have implications in what concerns the model that I will discuss. Now, a very influential paper came out in PNAS in 2008 based on some economic behavioral experiments done by Manfred Milinski and collaborators. This involves actually a repeated game in which groups of 6 individuals were put together and they were supposed to play for 10 rounds. To begin with, they were given 40 euros each, and they could, at every round of the game, they could do one of 3 things. They could either contribute nothing, that was seen as the selfish strategy or the selfish behavior. They could contribute 2 euros or 4 euros. And the idea is that there was the cost for saving the planet was 120 euros, and the experiment was formulated in the context of climate change. So there was a cost to save the planet. And to meet this cost, you would have to sum up the contributions through all these 10 rounds, through all these 10 rounds. So if at the end of the 10 rounds you would have more than 120 euros, the planet was saved, everybody would be happy, and you would go home with the money that you had in your pocket. Otherwise, this would not happen, except with a residual probability. That would be this probability that even if you would not meet the target, maybe for some strike of luck, you could get the planet saved. So with this probability, at the end of the day, you could still walk away with the money. And the results actually, to cut a long story short, show that actually risk is very important. So risk here is the complementary of this probability that you get away with the money, even if you don't meet the target, right? And so when the risk is very small, meaning that with a high probability you just go home with the money, you see no group was actually reaching the target of 120 euros. When the risk was 50%, you had somewhat larger contributions, and when the risk was very high, then you had a significant number of contributions, so a significant number of groups were able to meet the goal. Now, this experiment has been replicated in by other groups, pardon me, in particular, and with some variants, which I think are pretty important. One of them is this idea of letting individuals, before they actually engage in taking a decision, they may announce what they are going to do. And this announcement is not binding. So it means I can say, I will contribute 2 euros, but then maybe I don't contribute, or I contribute a different amount. But the fact of the matter is that this so-called pre-play communication actually enhances cooperation. The result is not amazing, unfortunately, but it does help overall cooperation in exactly the same setup. And then there's quite a negative result in 2012, saying that if the target that you have to meet, this say 120 euros, is uncertain, then actually the cooperation breaks down. After a certain level, cooperation will break down. A certain level of uncertainty. And this was demonstrated in a variant of this game in which there's no repetition, not 10 rounds, it's just a single round, but people have just this idea that first they contribute, and then there's a fortune wheel that will tell you what the target is, and then you will see if you meet the target or not. And under this uncertainty, cooperation breaks down. I think this is an important problem. This paper was published in 2012, and as I just said in the beginning, now people are discussing it on an everyday basis, this problem of threshold, so-called threshold uncertainty. So experiments tell us basically that risk is extremely important. If risk is not perceived to be high, then there are very little chances for cooperation to be sustained. And of course, I didn't go through the argument, but actually individuals do not play rationally in these experiments, and actually their decisions also change along the way. So during this 10-round period, individuals behave differently. Of course, the experiments have some problems of their own, not problems but limitations, in the sense that they are expensive, they are difficult to run. You have to be very careful in controlling for many different variables. So usually, of course, because they are expensive, they involve small groups and only one group size. There's also a very finite time horizon for the investments, and we can say, and consequently, we can say very little about groups or about group size, for instance, or we can also say very little about how this applies to global summits, for instance. So the idea that I want to push here is not to criticize actually the experiments. I think they are very important, but on the other hand, to say that it would be nice to have a theory that complements these experiments. I think this is the main idea. And that's what we actually started doing. So we set up a very simple, conceptually a very simple model, an evolutionary game theory model, to deal with this problem of climate change. And in our group, we have some experience on dealing with this threshold public goods games. And so what we did is to set up what you can imagine here as an infinite population to begin with. We will also deal with finite populations in a second. And then out of this infinite population, in a way that has been already discussed before, you randomly sample groups of size n, and for each of these groups of size n, individuals engage in a threshold public goods game involving a threshold n, right? So in this case, you need to have at least m individuals. So you have two kinds of strategies in the simplest setting. Those are the cooperators and the defectors. The cooperators, everybody starts with an initial endowment B, and the cooperators pay a fraction C of this endowment to contribute into the common pool. And if you have at least n cooperators in each of the groups of size n, then the public good will be realized, and they will get whatever is left. Naturally, the cooperators get B minus CB, whereas the defectors will get B, right? Because they contribute nothing, as usual, to the public good. So the defectors are always doing better off. So this is the basic game, but then we add a risky twist to it, just like in the experiment. So even if you don't beat the threshold, then with a certain probability you can still get away with whatever benefit or whatever payoff you had, right? And so with this risk, which is just 1 minus r, you can actually write down the payoffs of a defector in a group with k cooperators. The group has size n, and the threshold is m, and then the payoff of the defectors and the payoff of cooperators is, of course, the same minus c times b. And then we can, of course, study the evolutionary dynamics of this system, both in large or infinite populations, if you wish, using replicator dynamics formulation, or in the case of small populations. And the idea is that if we are talking about, if our population is of country leaders, we have populations of the size of 200, of the order of 200. So these are small populations. And consequently, we should change the formulation to take this finite size into account explicitly, and we can do that using the stochastic birth death process, which can be of any kind, but we were careful to do the two dynamics in such a way that when you take the infinite limit of the stochastic process, you get into the replicator, into a modified replicator equation. And so we will assume all mixed populations. We have also done cases in which we have network populations, and the results, I will just briefly discuss that. So the dynamics is controlled in the infinite population case by the replicator equation that you all know. We have only two strategies, so x is the fraction of cooperators in that population. This g of x is what we call the gradient of selection, which tells us in which direction evolution will be favoring if you wish, the next step, given that you have a given fraction. The fitness is related to payoff by the usual binomial sampling in an infinite population. Of course, if the population is finite, we have to take into account the finite size effects. We have to replace the binomial by some hypergeometric sampling. And of course, this is taken care of. But then we have the fitness, we can put it in the equation, and then we have to worry about what is the sign of g of x, right? So if g of x is positive, then for a given fraction of cooperators, this means that the dynamics will push me towards increasing the number of cooperators. If g of x is negative, then the drive will be towards decreasing the number of, or the fraction of cooperators. And now, with this model, we can just look at what happens as a function of risk. So this is for an infinite population. The group size is 6, just like in the experiments. The threshold is half the group size, just like in the experiments. And we just take different values of risk. So each line is for a different value of risk. And what you see, let's see if I can do it like that, what you see is actually that for no risk, in the absence of risk, you actually have the typical scenario of the trajectory column. So g of x is always negative, which means that selection will put you down to a no cooperative scenario, right? As you start increasing the risk, then you start developing this little hump here that will bring you 2 points here, which are actually a coordination point on this side. Remember, we are in infinite population, so this is a deterministic dynamic. So there are no fluctuations here, no noise here. So there's a coordination point on this side and a coexistence point on that side. So the thing is that if you start with enough cooperators, then the dynamics will move you into a large fraction of cooperation, but not 100%, right? And this gets better and better the higher the risk. So the model, however simple, gives you this idea that indeed risk makes the whole difference in this process. If you have high risk, you have a chance for cooperation. In the absence of risk, cooperation, there's no chance for cooperation. Okay? So this is kind of the first result of the model. Of course, that with this model, now we can do whatever we want, right? We can change the group size, we can change the threshold, we can change the population size. There are many things we can change and study exactly the same behavior, for instance, as a function of risk, but for all these conditions, which, since this is analytic, is much cheaper than doing the experiment, right? So, for instance, if you do this, if you study the evolutionary dynamics as a function of the threshold, you see that the higher the threshold, the better you get into the coexistence state, but the higher the price you pay for coordinating, right? So the higher the number of cooperators that you have to start with. This is actually, even in the deterministic system, this is actually not too bad, because you can imagine from the beginning that there will be quite a few countries that will be interested in cooperating. So maybe the initial fraction, if we are talking about countries, the initial fraction may not be the ultimate problem, right? But this is, of course, this is just a remark. We can also tell, for those that do not understand this graph, I will be very happy to explain it in detail. It's kind of quite involved to call this cooperation. But we can also just take a finite population. Here is a finite population of 200 individuals, and just study the evolution as a function of risk for different group sizes, right? And as usual, if we reduce the size of the group, cooperation will be easier, right? This is also a well-known result from public goods game, from threshold public goods games, but here, just with you see that the emergence of cooperative states will happen for lower values, for lower and lower values of risk, depending on the group size, right? The other interesting result is what you get when you now fix the group size. So before we had a fixed population size and we were changing the group size. Here we are fixing the group size and we are changing the population size. So if we have the infinite population, we have the solid curve over there. By the way, this is for highest risk, for risk 100%. And if you then start decreasing the population size, making it closer and closer to the group size, then the levels of cooperation start going down up to the point that, of course, when the population size is equal to the group size, you have no cooperation at all, even for 100% of risk. And this tells you basically that if you want to do these negotiations, if you want to have these people together, maybe you should not have everybody into one single group. Maybe you should break up the groups, because smaller groups will favor cooperation. It will always be easier to coordinate in smaller groups. So, to cut the story short, this evolutionary game theory approach to the climate change problem basically tells you that risk, from a more technical point of view, risk transforms n-person prisoner's dilemma into an n-person coordination problem. And coordinating to this common good will actually be better achieved if we get many small groups. In fact, we did also some studies in which we have a diverse group size, linking different individuals through a network, and we show that actually cooperation is even better, so coordination is easier, and coexistence happens for a larger fraction of cooperators when you have individuals wired through a heterogeneous network. And with a high perception of risk, this is important, so low risk, there's no solution to the problem. And then stringent thresholds mean higher F. So the idea is that you have small groups, and these people actually agree that you need to have a lot of cooperation in these groups to get on. Okay. So this is the setting. Of course, this is one should never lose track. This is an extremely simple model, right? And so humans are not like this. Humans are much more complicated, much smarter, and of course, not rational, but much smarter. And so this means actually that this is kind of a baseline scenario. On top of this, there will be many things that you will put on which will decorate this model and will bring it closer and closer eventually to reality. But at the core level, this is the kind of dynamics that you might expect, and which is, being remarkably simple, I think gives you quite a bit of insights. But still, we can study other things that can actually affect the overall dynamics of cooperation. And I want to talk about these three things in the following, if I have the time. So one is this threshold uncertainty problem. The other is this conflicting policies between rich and poor countries that have been argued. And I think that's an interesting issue. And I touched this in two ways. We will see in a minute. And then the idea of what is the role of sanctioning institutions in the whole of this process. And when I'm talking here about sanctioning institutions, you should always think in terms of what you've heard up to now, in terms of full punishment, right? The thing is that I will talk about global institutions and local institutions. You'll see that in a minute. So this idea of threshold uncertainty, as I say, comes back to this paper, to this PNAS from 2012, where they say, well, there's a critical value of the uncertainty above which cooperation simply collapses. And this in our model is extremely simple. Basically, basically what you do is that instead of having a sharp threshold M, you just diffuse it over a certain interval, right? So you say you're not sure. This means that, for instance, for every group that you set up, you throw a die, and then you will see if the threshold will be above or below this M with an average of M. And what you see here is just a comparison between the gradient of selection for a selected case in which you have no threshold uncertainty. So this is a typical scenario with coordination and coexistence, if you remember. And then you just put a finite threshold, a finite width uncertainty in this threshold, and suddenly the gradient becomes fully negative. So indeed, you increase the uncertainty and cooperation may collapse. Okay. Of course, if the uncertainty is small, you will still have a somewhat worse scenario. But the message is that uncertainty will always bring you down in terms of cooperation. This is the gradient of selection. This is the stationary distribution, which tells you basically the fraction of time the population spends in each of the possible configurations. Remember that I'm doing a trick here. I have a finite population, so this is not strictly continuum, right? I'm slicing the population into finite intervals, but you see this is the stationary distribution for no threshold uncertainty, and this is the stationary distribution for threshold uncertainty. And if you look at it in terms of cooperation, you see is that actually you need a much higher risk for cooperation to emerge in the presence of threshold uncertainty. So if you put this thing in the present context, the present context is, one, there's a lot of uncertainty, two, there's an overall perception that the risk is low. And this is bad news, right? Because this means that risk is low, so you are somewhat here, and then uncertainty is high, so it means that you are in the most unfavorable scenario. So there's a lot to change. And as I say, of course, there's also this story of wealth and of threshold uncertainty has been in the headlines very recently. So people are kind of waking up, and there are actually kind of ironic proposals of what to do with this threshold uncertainty. I think people really need to think a little bit better about this. But anyway, otherwise we are not going anywhere. So let's now talk about the third topic, which was this idea of wealth inequality, right? So you have rich countries, you have poor countries. There have actually been experiments performed with the groups in which individuals were playing the role of rich and others were playing the role of poor. But some of these results are interesting. And of course, these experiments are very complicated and they are subject to a lot of criticism, actually. But the thing is that one of the things that we should not overlook is that there are many more poor countries than rich countries. If it's just the simplest calculation you can do is just to take the GDP of all the countries in the world and look at how many poor countries you need to make the GDP of the remaining countries. And that will give you this breakup of 20% of rich countries to 80% of poor countries. Of course, the truth is not there. There's a blur, right? There's a distribution of wealth, which is, by the way, kind of power law, but but we are not at that level of sophistication. We still want to do the calculations analytically, so we take two groups. We take the rich and we take the poor. But we take them to be 20% of the population will be rich, 80% of the population will be poor. They will mix up in groups in which the composition will be diverse. It's not always like in the experiments that you had 50% rich and 50% poor. Here you will have all possible fractions. And of course we also controlled for what happens if we impose that the mixing is 50-50 and the results change a little bit, but the qualitative message doesn't change that much. So another important aspect of this particular model that I'm going to talk here is that the rich people will pay the same, the rich individual countries that contribute will contribute with the same fraction of their wealth that the poor countries contribute. So of course the rich contribute more than the poor. Okay? There are situations in which this may not be the case. Even in experiments, this has also not been the case. And then, of course, as usual, we assemble them randomly. And now, this is an important part of this is an important ingredient of the model. With a probability H, which is this homophily parameter, this means that individuals, when they revise their strategy in the imagined replicator dynamics equations, what they do is that they only look at those of their kind. So if I'm a poor country, I look at what's the fraction of cooperators and defectors among the poor, and if I'm rich, I will only look at the fraction of cooperators and defectors among the rich. This is for H equals to 1. For H equals to 0, we are in the normal situation in which you look up to the entire population and you sample what you're going to do from the entire population. Okay? This is important, in my opinion, this is important because this is a political issue. Very often, many countries defend that they should kind of take joint action, and consequently they are more likely to be influenced by their own group than by the other. And so to cut a long story short, I will go a little bit more into the details. You can think of this group achievement as cooperation, as the overall levels of cooperation in this population. And here, I'm not distinguishing between rich and poor, right? There will always be this fraction of 20% of rich and 80% of poor, but I'm summing up the number of individuals that cooperate among those two groups and those that do not cooperate as well. And the blue curve shows what happens under wealth inequality, so when you have rich and poor, and without homophily, right? So everybody can imitate everybody else, and this is the blue curve without wealth inequality, so when everybody gets the same, and of course the payoffs have been normalized so that we can actually compare the two curves, you get this behavior here. So you get an emergence of cooperation for much higher risk, right? And when you have homophily, so this means, in this particular case, it's the highest possible homophily. And by the way, this transition is highly nonlinear. The transition from h equal to 0 to h equal to 1 happens somewhere around h 8.8 and h equals to 0.8, and it's highly nonlinear. But in any case, for h equals to 1, then you have a significantly inhibition of cooperation, okay? So this is to cut a long story short. How do we get to these numbers? So this is a plot for this is a finite population. I guess it's about 100 or 200 individuals. So here is the fraction, in fact it's 200 individuals. So here is the fraction of poor, right? And here is the fraction of rich, or in fact the absolute number of rich. And now my face space lives in this rectangle where I have a finite number of cells, because these are all the possible configurations of my system, right? Each cell in this peculiar simplex, if you wish, tells me how many cooperators among the poor and how many cooperators among the rich there are. And then the shading of this rectangle gives me the prevalence, the stationary distribution. So it tells me the fraction of time the population spends in each state. So the darker the area, the more time the population spends there, and the brighter the area, the less time. And the arrows give you the two-dimensional gradient of selection, which tells you exactly the same message as before, but in a finite population. So it tells you the probability that you move onwards into cooperation or backwards out of cooperation for each given state. So this will be, of course, a two-dimensional vector, and you can draw these vector fields. And what you can actually see, and it's kind of summarized here, this will be too fast to analyze, but in any case, is that basically in the absence of homophily, remember that h equal to 0 and risk equals to 30%. In the absence of homophily, what happens is that actually the poor, they actually cooperate more to begin with than the rich. But despite the fact that when they move down, the fact that they cooperate more in the absence of homophily makes the rich also cooperating more. And when the rich cooperate more, they change effectively the game that the poor are playing, make the game that the poor are playing more and more of a coexistence game with a better equilibrium, stable or interior attractor, and consequently the dynamics wraps up and leads the population to that state in which you see quite a good deal of poor actually cooperate and most of the rich actually cooperate. And this scenario actually changes. And you see, I have here three plots for different values of the homophily parameter. So this is no homophily, 100% and 70% of homophily. And you see that, in fact, what happens basically is that the rich sustain and cover up when the poor stop cooperating, and the poor will stop cooperating more when homophily goes up. The rich kind of compensate for the under contributions of the poor, but up to a certain point. And this point will be depending on the risk. So if you see, this is the scenario for risk 30%, and look at what happens for 20%. So for 30%, you have a lot of cooperation in the absence of homophily. That goes basically down. Here, the rich are still contributing. The poor are no longer contributing there, right, under homophily. But in the same three scenarios, for a lower risk, the rich will not compensate at all for the poor. So the cooperation simply collapse. So again, no matter what the scenario is, risk, I think, is the determinant factor here. It's very important that people perceive that the risk is high, because under those scenarios, cooperation will always be more favorable. Now, this is a very mixed message, by the way, but I leave it up to you to figure out the implications of this message. But look at this situation. This is homophily equals to 1. So rich only look at the rich, poor only look at the poor. And then you have here a scenario in which this is the scenario from which you start. And then what we do, and as you see, there's basically no cooperation here. And what you do is that now you say, well, let's say that 10% of the population, say among the rich, they are what we call obstinate cooperators. No matter what, they say, look, we really have a problem. We are putting the money. We are cooperating, no matter what, right? So these will never change their mind. And this is what happens. So you see, the phase space gets a little bit shorter. You don't need to worry about here, because these here, they are always cooperating. So you have only here. And still, when you have the obstinate rich, still it doesn't really help that much. Cooperation will be very, very small. Okay? But now look at what happens when you put 10% of the poor. So if 10% of the poor just say, no matter what, we just contribute to the public good, then actually you are not too bad off, comparatively, right? So even in the presence of homophily, the fact that some of the poor individuals behave obstinately and never change their mind actually promotes quite a lot of cooperation. This is an effect that has been found actually elsewhere, for instance in the context of indirect reciprocity, but here is also present. So our results, what our results show actually is that the prospects are not that bad, even in the presence of wealth inequality, if we take this distribution. Thank you. The thing is that you still need to have a high perception of risk, and you need to be you need to have targets well defined. So let me go to the last topic in this last 5 minutes. So I think I'm going to jump over some slides, but I can discuss with you whatever you want. So the idea here is what happens if we now look at institutions. And we all know that these institutions can be problematic. There's a second-order free riding problem, etc., etc. But going over all that, let's look at the institutions. Our biggest curiosity here was to understand what happens when we compare two kinds of sanctioning institutions. One that is local, and another that is institutions that work locally for each group, or you have just one single institution, like say United Nations, that sanctions everybody at the same time. So here, because we have these punishers, we have three strategies, but unlike most of the discussion that has been done up to now, I would like to stress that we have a N% coordination problem for the public goods game, but we also have a coordination problem for the punishers. And the reason is actually very simple. It's because if you do pull punishment without a threshold, this means that one individual, one cooperator will be enough to set up an institution, which is kind of strange. So what we do is that we impose that there's a minimum number of individuals that have to contribute before an institution actually shows up. And so the model is, with this proviso, the model is very similar. We have cooperators, defectors, and punishers, and now we can look exactly at the same evolutionary dynamics. Of course, now my simplex will be a triangle. I do not have wealth inequality here, but when we look at local or global institutions, The difference is illustrated here. So under a global institution, the number of punishers that counts for my threshold gain is going to be somewhere between 0 and the total population size, whereas for the local institutions, the number of punishers that matter are those that live in the group, so between 0 and n, right? And for reasons of comparison, we'll look at ratios that are equivalent. So we look at fractions of punishers in a group that are equivalent to fractions of punishers, in the population. So this is just for the sake of comparison. But in this case, it means that you can have a group, in the case of local institutions, you can have a group in which punishment is effective, because there's a sanctioning institution in that group, but in all the others there's no sanctioning institution, just because the composition of the group was not enough to set up a sanctioning institution. So this is quite a fundamental difference. And now what we do here is that for each case, so you see we have three strategies, we have this simplex, the convention is the same, the arrows are the gradient of selection, the shading gives you the fraction of time the population spends in each possible configuration in the simplex, and what we do now is that we ask, given the stationary distribution that we compute, then we can actually find the probability of, for each specific configuration, we can compute the probability that a group with this configuration will actually reach the public good and the institution will be met. So we can compute the so-called institution prevalence, which is an average over the entire population, weighted, of course, with the stationary distribution, and then we can do the same for the group achievement, which is basically the levels of cooperation in the population. And the results are here. I must be running out of time. Am I correct? 2 minutes. Thank you. So here, this curve, I think, this plot, I think, it's really amazing. So you have actually three curves. The blue one is what happens as a function of risk to these levels of cooperation. So this is group achievement with local institutions. This is what happens with one global institution. That's the red curve. And the black curve that is underneath is what happens when you have no institution at all. So even if you have a global institution, what the model is telling you is that it really doesn't matter that much. You don't get much cooperation. But if, on the other hand, you try to solve the problem locally, if people get into a group, they agree on finding out someone that monitors the behavior of the individuals in the group and sanctions individuals in the group, then the result is actually very different. So, and here is the prevalence of institutions, which is, of course, much higher also there. These are results for low risk and for high risk. But the message, actually, is that one should really, in this, never forget, in this very simple scenario, one should always, if we want, so the way I see this problem is basically setting up the most favorable scenario for cooperation to thrive. Then, of course, there will be much more on top of this that cannot be taken into account in the model. But the idea is that if you want to make it the most favorable scenario, then you should actually think about these problems locally and act actually globally in your mind. And actually, this is something that, going back to Eleanor Ostrom, I think she writes it down in quite a simple way, that she writes that given the severity of the threat, and she's talking about climate change, simply waiting for resolution of these issues at a global level, without trying out policies at multiple scales, because they like a global scale, is actually not a reasonable stance. And so I think this is very much the idea that is captured by this issue of setting up local institutions as opposed to global institutions. So if I'm allowed to give you a takeaway message, my takeaway message would be think globally, but act locally. Okay? Thank you.
Please. you very much for a very nice overview of modeling of climate change problems. I was wondering, you would emphasize that small groups are more conducive to reaching high levels of cooperation. I was interested in, when you have these small kind of collective risk or public goods interactions, then the benefits are also paid out to these small groups.
Yeah.
But in the climate change problem, we face a situation where the benefit is only paid out if on the global scale we achieve a certain certain level of contributions. So how does that factor in?
That's correct. So you can think of this as that these local groups, they are not really solving the global problem, but everyone is solving their share of a public goods. Okay. So if they succeed, everyone will succeed. So maybe what I'm missing here is to have some kind of a feedback into whatever happens in the other groups. But this is indirect. So the idea is that we break up the problem into smaller problems, and everyone tries to do their own. And at the end of the day, the sum-up contribution will be also better off. I think this is the idea that is also encapsulated in this statement of Elinor Ostrom. You have to do your thing, and then you have to believe at a certain point that overall this will happen. So this public good is not strictly speaking the global public good. It's a local share of the public good. It's viewed as a local share of the public good. Okay?
Yeah, I think that's just very important, because you're basically changing the game. You have to reinvent the climate problem on a smaller scale, so that you can define some kind of benefits to a local community in order to solve the bigger problem.
Now, is this wrong? I don't think it's wrong, and the reason is that if you look now at the discussion that we are witnessing, for instance, just last Thursday in Nature, the issue is exactly this. So the models give you forecasts. These forecasts are uncertain. Uncertainties are different if you talk, for instance, in impact on methane and CO2 and other effects. And the contributions of different countries at the regional level will also be, and the impact of these contributions in the global problem will be very different. Even with technological means to deal with the problems will also change from place to place. So actually, I think this is the way people will have to go, is to break up the public good into local samples, if you wish, of the public good. I think this is actually the way things are moving, because one thing is sure, there's no silver bullet that's going to get you out of the uncertainties. So this is clear. The models are way too, there are lots of errors in parameter estimation and even in numerical integration of the algorithms and so on. So there are intrinsic uncertainties in the forecast that you cannot avoid. So people are saying we have to fictitiously define the thresholds. That's it. Let's take the minimum. I don't care. Let's take the minimum. Let's discuss just the minimum. That's what people are saying. But I think that it will come to that problem, right? We have to solve the problem in each one locally at their own way with the best means they can.
Thank you very much, Jorge, for a wonderful overview. It was really very clear and crisp, and your initial worry that one couldn't follow was entirely unnecessary. They're very nice.
Thank you.
And I think I want to stay on the point that Christoph has raised. I very much agreed with, as far as I could understand, your analysis in the first three parts. And I have the same concern as Christopher, so let me try to paraphrase it a bit more to give you another chance to react to that. Of course, we can assume payoff structures, and that's what you have done, and they can be localized in our hypothetical game. The question is how that substantively relates to reality. And in my naive understanding, we have very little impact on the distribution of benefits because they operate through the global concentrations of certain chemicals in the atmosphere, and there's really no mechanism I can think of to regionalize the return on investment here.
Mm-hmm.
So how would you conceptualize the model in your fourth part under that premise?
Yes, well, I think it doesn't apply perhaps only to the fourth part, but I think that the idea here is that, for instance, think of the case, this actually is even best model if you put some underlying network, but think, for instance, that of attempts to solve the problem by using a specific technology, right? It could be by reducing greenhouse gas emissions by using alternative forms of energy, or sequestrating carbon as is being done elsewhere. So you can actually define groups that set up targets and then can actually cooperate to invest in a common technology, or even in the development of a common technology. This is gives you naturally a fragmentation of the public goods problem, but the return is not immediate. And I think this is the problem. So there's a time lag here, that's clear, but this will be too complicated, I guess, to put. I mean, you know what happens when you have delayed differential equations. We all know very well what happens, and things will be more difficult, but that's, I think, one of the points. And the other, of course, is discounting. Right? That we are all overlooking, except you.
In your last section of your question about punishment, does the size of group affect the final result? Because in our recent experiment of the institutional punishment in the climate change field, we have proved that the final result is robust against the size of group. Just related with the risk and the probability of punishment.
So, yes.
Is your result is related with the size of group?
Yes, but in the case of
Just for the punishment.
that's right. But we do not have punishment there. We didn't study the behavior in terms of group, but I would imagine that the changes would not be would keep in line with a variation from also in terms of group size. So, but of course we have to look at the. I have no idea of your results, but we have to look at your results carefully, also to see in which way changing the group size is maybe not changing other parameters of the game. There are different parameters. We can certainly do exactly the same combinations that you did, and we can compare the results, and I think this would be great.
This is very interesting. One of the question is if the non-cooperative players increase, the sanction costs also increase. So the sanctions costs for the individual player and all institutional also may increase. So with I think the cost, if the cost of sanction is increased, this might overhead the benefit received. So is that enough to maintain the cooperation?
I'm not sure that I understood your question. I'm sorry.
I can, with the increase of the number of the non-cooperating players,
Yes.
The sanctions cost also will increase. Sanction cost of sanction or punishment. Yeah, it also increased. So the cost may be overhead the benefit received, or the institutions may not be able to pay much more higher costs to pay punishment.
That's right. That's right. So if the number of defectors is increasing,
Yeah.
the chance for setting up institutions is going down, of course. So it will make things much more complicated. That's true. That's exactly what we have.
You have how to resolve this problem? Which mechanism could resolve this problem?
I think the easiest way. So I think the easiest way to get rid of that problem is to increase the overall perception of risk. at least in the model, that's the easiest parameter that you can use, because when you increase the perception of risk, you are shifting the equilibria to a more favorable scenario, which means that the natural tendency that you were speaking about for the number of defectors to increase will be inhibited. And consequently, there will be a larger margin for cooperators to prevail in the population, and when that happens, punishers will also be there to set up institutions. But of course, I should point out, I didn't do that, but I should point out that the second order free rider problem here is there, as always. So in a situation when cooperation takes over, punishment stops being necessary, and therefore you are going down into full cooperation, which then is prone to be invaded again by defectors. But this is the story that a lot of people have devoted a lot of very useful time recently dealing with, right? So I think that's the trick. Let's hope that people understand it's really a high-risk situation.
Okay, thank you very much.